Hello, hello, AP Stats children. So today we're going to go ahead and start with our second lesson, and I'm going to be honest, this one can be funky and weird. So track with me if you need to watch the lesson, parts of it again, totally understand, but let's do this. So last lesson we started with scatter plots. I had you guys graph a scatter plot by hand, and we talked about how to describe scatter plots with form, direction, strength, and then if there are outliers, you need to mention there are outliers. So today we are going to focus on an idea, actually a value called correlation. And correlation so wisely is abbreviated in statistics with an R because of course it is, naturally. So correlation is going to kind of help us describe scatter plots, as you're going to see. So to start off with today, I have an example for you that I'd like you guys to work through. So I'm going to set up the example, have you guys pause the video, compare your answers with what I get in the end, and then we'll move on. So here's our example. It says a student wondered if the number of hours studied would increase a person's test score on an AP Stats test. She gathered the following information from her AP Stats class. So she gathered presumably 8 students and asked them how many hours they studied and their score on a test that they had recently. So what I would like you to do first is this. I would like you to go ahead and make a scatter plot with the data that you're given from the table. And then I would like you to as well go ahead and find a couple of things. So first of all, that X has an equal sign on top. That's weird. So first of all, we're going to go ahead and make hours studied our explanatory variable because what we're saying is we think the number of hours studied would cause you to have a certain test score. And we'll go ahead and make your score on the test the Y variable. And what I would like you guys to do, in addition to making the scatter plot, is I would like you to find the mean, that's supposed to be just an X bar. I would like you to find the mean amount of hours studied, and then I would like you to find the mean amount or mean score on the test separately. And then I'd also like you to find the standard deviations of each. If you do not remember how to do that, what you can do is you can put hours studied into L1, and you could put scores on your test into L2. And remember, or maybe you don't, or maybe you didn't do this, but if you want to get a list of summary statistics, so things like the mean, standard deviation, you can even get median, quartiles, all of that. What you're gonna do is you're gonna put all your data into L1. Oopsie, so L1. And so you type in the hours studied into L1. And then after that data was entered, you would press stat. Oh my gosh, Microsoft Word, I want to punch you and throw you off a cliff. Yeah, okay. Sorry, I shouldn't have erased that. You're going to press stat. And then you are going to scroll to the right to where it says calc. And the very first thing that should be highlighted is going to say number 1, which is 1 var stats. And so you're going to press enter after that. So stat, calc, it should say 1 var stats. You're going to press enter. When you do that, it's going to ask you for a list. And the list that we're going to start with is L1. So hopefully your list says L1. If it doesn't, then you're going to just press second and the number 1, and it should put in L1. After that, you're going to go down to calculate and press enter. And it should give you, the very first thing it should give you is a mean, which is what we're looking for here. And then if you look down, you should see an S sub X. That's your standard deviation. I want that as well. Okay. So to recap, I would like mean and standard deviation for hours studied. I would like mean and standard deviation for the scores on the test individually. And then on top of all that, I would like you also to create a scatter plot with this data. Okay? So go ahead and pause, take some time to do this. This should take a good 10 minutes. So go ahead and make your scatter plot, take your 10 minutes, get your mean, standard deviation, and then we'll resume the video together. Okay, so pause. Okay. So you should have a scatter plot that looks pretty similar to mine. Again, hours studied should be on the x-axis, test scores should be on the y-axis. Just a quick housekeeping issue. Make sure you label your axes. If you're asked to make a scatter plot on the AP test and you don't label your axes, you would go from full credit to automatic partial credit. So something super easy, something super simple, please make sure you label your axes. Okay, so we have hours studied versus test scores, and then we should also have our mean and standard deviation for hours studied and mean and standard deviation for test scores individually. So these are, obviously I rounded, these are the mean and standard deviation for hours studied, 4.63 and 2.33. Mean and standard deviation for test scores, 43.75, 23.26. Okay. So great. We hopefully have done that. So we're going to go ahead and move on. So let me tell you kind of what the goal is for today. So first, let's check out our actual, our scatter plot itself. So if I asked you to describe this scatter plot, I would want you to talk about form, direction, and strength. So in general, let's talk about the form of this. Yesterday's example, frankly, was pretty linear. Most of those points kind of lined up, if you will. This guy, I would argue, is still linear. Like if I drew a line in the middle of your points, most of the points are kind of lining up with that line-ish, but it's not as strong. The points are a little more spread out. It sort of looks a little more like a blob than the data did yesterday. So hopefully you're with me there. But one thing for sure I think we can say is as the hours studied increases, it appears that the test scores also tend to increase as well. Now there's exceptions, like this poor person who studied for 4 hours and still got a 20 on the test, like that sucks for them. But for the most part, the longer you study, the higher your test score seems to be. So in general, if I were summarizing the form, direction, and strength of this scatter plot, I would say that the form is roughly linear. So it's linear. I'll say it's roughly linear. So it's not very strong. Roughly linear, and I would say that it is positive. Okay. So what we're trying to do today is we want to actually get a number that measures both the direction, whether it's positive or negative, and the strength of the graph that we have. And so that's what we're going to be deriving today. So we are looking for a number that tells us the strength, exactly how strong the relationship is, and whether the relationship is positive or negative. And so I'm going to show you today how we come up with that number. But from today forward, you're never going to have to actually derive this number. It will be given to you in problems. So let's go ahead and do it. Okay. So this should have seemed random to you. Why am I finding mean and standard deviation? What does that have to do with scatter plots? Well, that's sort of on purpose. It should have seemed a little out of the blue for you. What we're going to do next is we're actually going to find the z-scores of each of the hours studied and the test scores. And hopefully you remember what a z-score is, but if you don't, which by the way, every year at this time, even though you just did z-scores, every group of kids I've ever had is like, what's a z-score? So let's do that. To get your z-score, you're going to take the value that you're interested in, subtract it from the mean, and divide by the standard deviation. So let's start with our very first value here, and I'll put this in something fun like purple. Okay. So let's start with the number 1. So for hours studied, the first value we have is 1. So one human being studied for 1 hour. So my z-score for that one person, so z-score for 1 hour studied would be 1 minus the mean, and the mean for my hours studied is this 4.63, so 4.6, oopsies, oh my goodness gracious, word, you're killing me. Okay, 4.63 divided by the standard deviation for hours studied, which is 2.33. And so if I plug that into my calculator, I do 1 minus 4.63, and then that answer divided by 2.33, I should end up with, let's see here, negative about 1.6. Okay? So what I would like you to do right now is go ahead and find your z-scores for each value. So find your z-scores for, you just found it for 1, so I'd like you to do it for 2, 4, 5, and 7, because those are the rest of the values. There is a shortcut to do this on your calculator, but it's sort of awkward for me to describe it to you without actually showing you, and TI's simulator for this computer is like exorbitantly expensive. So that being said, while I am talking right now, you guys can go ahead and calculate those z-scores. Actually, you know what? No. You go ahead and pause this, calculate the z-scores for both hours studied and test scores. You can press play. We'll resume this and then get going. Disclaimer, because I don't know you, but I know you. You're going to just not press pause. You're just going to continue going and then copy what I write down. That's fine, but I need you to actually go through the motion of finding a z-score. So if you don't want to do all of them, that's cool. At least do it for 2. Do it for this guy. So do it for the number 2. And then maybe for the scores on the test, do it for 50. Okay? So if you do those 2 z-scores yourself, then you can copy the rest of mine. That's totally fine. Okay? So go ahead and pause this. Do as many z-scores as you can, but for sure make sure you do 2 and 50, and then resume it when you are ready. Okay. Oh, I didn't pause mine. Shoot. Okay. Well, now you got to watch me write that. I hope that was riveting for you. Okay. So I have all my z-scores. And again, if you hopefully did this yourself, the z-score for 2 should have been about negative 1.1. And the z-score for 50, a score of 50, should have been 0.3. Okay. So now I have all of my z-scores for hours studied and for test scores. So now for realsies, I would like you to actually go ahead and pause this and create a scatter plot. So you're going to make yet another scatter plot, but instead of the original data of hours studied and test scores, you're going to make the scatter plot out of these z-scores. So you're going to put the z-scores for hours, oh my gosh, for hours studied on the x-axis, and your z-scores for test scores on the y-axis, okay? So go ahead and pause this video, create that scatter plot, and then I will resume mine as well. You can compare with mine, and then we'll talk. Okay. One quick thing, this isn't quite done yet because when you're actually making a scatter plot, if you notice the values you're trying to make are both negative and positive, and that's not usually what we are used to graphing when it comes to a scatter plot. So I am going to label my axes just like pretty much I would label normal numbers, except for I'm going to look at negatives. So in this case, for hours studied, my lowest value is negative 1.6 and my highest value is 1. So I'm going to start my first value here at negative 1.5. And then it looks like, let's see here. I'll go by Yeah, we'll go by 0.5s. So I'll go negative 1.5, negative 1.0, negative 0.5, 0, positive 0.5, and then 1. So we'll do it like that. So I'm starting with negative 1.5, leaving myself some room, and then going all the way to my maximum value of 1.0. And then for my y-axis, I will do exactly the same thing because, again, my lowest value is about negative 1.5. My highest value is about 1.6. Okay? So go ahead and pause this. If you haven't made the scatter plot already, go ahead and do that, and then we'll check back. Okay. What you should notice from your graph is if you look at the scatter plot that you just made out of the z-scores, and if you go back to the original scatter plot, you should notice that the points from the scatter plot are roughly in the same positions. So for example, see how I've got these three kind of lined up here? I should have the same thing in my z-score scatter plot here, and I do. So both of those graphs should pretty much look identical. The only difference is the numbers that we're using to label. So our hours studied are 1, 2, 3 through 8, and then our z-scores are of course negative 1 to positive, or negative 1.5 to positive 1. Okay. So I'm going to again remind you of where we're going with this. So what I'm trying to do is I'm trying to come up with a number that describes the strength and the direction of these points. Okay, so here's what I'm going to do. If you notice, I should have a 0 labeled on both axes. And so what I'm going to do first is I am actually going to draw in like an x and a y axis centered at 0. So for example, I'm going to draw sort of a dashed line that lines up with 0 on the x, and I'm going to draw another dashed line that lines up with 0 on the y. Okay? And what we're going to do is we are going to sort of talk about these in terms of quadrants. So I'll tell you what I mean in just a second. But first, what I'm going to ask you to kind of look at here is this point right here, any of these points. Would you agree that this point is the z-score of x? So z-score of x, comma, the z-score of y. Hopefully you agree, because that's literally what we just did. We graphed the z-scores of x and we graphed them with the z-scores of y. So each of these points represents the z-score of x and the z-score of y. So what I'm going to propose is, what if I took those two z-scores and I multiplied them? So in this case I did z-score of x times z-score of y. I don't really care what the answer is. What I care about is, would that product, would z-score of x times z-score of y be positive or negative? And this is where our little quadrants come into play. Okay? So everything in this area, right here, in this quadrant, from here to here, everything in this area is positive. It's above 0 on the y-axis, and it's above 0 on the x-axis. Okay? So that means these two z-scores, zx and zy, are both positive, which means if I multiply the two positive numbers together, I should get a positive result, correct? Good talk. Okay. Well, what about this number right here? What result would I get? Would it be positive or negative? Well, it should be positive again, because, again, I have all of my values in this little quadrant are positive. Okay, let's go over to, say, this guy right here. What would the product, the two z-score product, be for this guy? Well, it would also be positive, because both z-scores in this area, in this particular quadrant, both z-scores are negative, and a negative times a negative is actually a positive. Well, what about this guy? Well, this product would also be positive, because again, I still have a negative z-score on the y-axis, and I have a negative z-score on the x-axis, and a negative times a negative is a positive. So hopefully you kind of get where we're going with this. So this guy originally was positive, this guy's positive. How about this guy? Well, he's also positive because both z-scores there are negative. This guy's positive. Oh, what about the other two? Let's go blue. Okay. What about this guy? What's this product going to be? Well, for this guy, his z-score for the x is positive, but his y z-score, because it's underneath this line, is negative. And a positive times a negative is actually a negative. And then this guy up here also is going to have a negative z-score, or z-score product, I should say, because this time the x z-score is negative, but the y is positive. Okay, so let's kind of tally this all together. So altogether, if I'm looking at the overall z-scores, so zx times zy, if I'm looking at all of the products, it appears that I have 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6 products that are positive, and I have 2 products that are negative. So overall, the overwhelming, if you will, z-score product, zx times zy, most of these are positive. So overall, zx times zy is positive. So let's backtrack for a second because I want to make sure that we understand this. So again, we made these points. I'll erase some of this stuff here. Hold on. So we made these points all out of z-scores of x and y. But in general, these points should pretty much line up with our original scatter plot. So each of these points represents a z-score for x and a z-score for y. If I multiply my two z-scores, I don't care what answer I get, I just care if it's positive or negative. Okay? So overall, because I have more positive scores than negative, overall, my z-score of x times z-score of y is positive. Well, this part, the positive negative part, is going to do what we wanted us to do. We wanted to find out a number that tells us direction. Well, this number is going to do that. It's going to tell us direction. And in fact, because there are more positive z-score products than negative, we know the direction is positive. Okay? So most of these points are kind of lining up in a positive trend, and so the overall is positive. Okay? So this number now that we just are, or this part of the z-score now that we found, is going to give us a direction. So let's start by kind of summarizing a couple things, and then we'll actually get the number itself. Okay. So this is correlation. This is an introduction to correlation R. Okay. R is a measure. It's a number that measures direction of, direction and strength. And finally, I'm going to give you the official definition of R. And hopefully after what we just did, this is going to make some sense. If you have to pause this and rewind it and listen to it again, totally understand. In fact, every year when I do this in class, I have to say it like 3 times. And by the 3rd time, about half of the people get it. So let's see how you do. So R is the average of the products of the z-scores of x and y. So I found a bunch of products of z-scores of x and y. In fact, this positive here represents the product z-score of x times z-score of y. So what R is it's an average of all of those products. So I'll say it again. So R is the average of the products of the z-scores of x and y. So I take all my x's and y's and I find their z-scores. I multiply each of their z-scores together and I average all of those out. That number gives me R. And then just for kind of, so you see an example of what values of R you can get, this would be a picture of a value of R is equal to 1. So if I had R equals positive 1, this would be the picture of that scatter plot. All of those points would be perfectly in a line, and that line would be going upwards. What then, if you had to guess, would this be? perfectly lined up, but this time going downward. What would R be? That's right, children. It'd be -1. So R is going to give us a strength and a direction. As far as the strongest value of R, it is some form of 1. So if you have an R equal to 1, that means that all of those points are perfectly lined up. And not only that, but if your R is +1, that means they're perfectly strong and they're going in a positive direction. If R is -1, they are also perfectly strong, but they're going in a downward direction. So what does it look like then if R equals 0? Well, that's a fun game. This is a picture of R equals 0. You have a flat line. This is another picture of R equals 0. What do you notice there? It's a blob. Not only is there no clear direction, I can't tell if this is going up or down. Most of the points are kind of all over the place. They don't even really make a pattern. So both of these together would be a picture of R equals 0. So perfectly strong is R equals positive or -1. Perfectly weak is R equals 0. So the closer your correlation value R is to 0, the weaker your data is. The closer your correlation is to positive or -1, the stronger your scatter plot looks. Okay? So that is what R is. That is its definition. You are, again, as I said, you are not going to ever actually have to find R yourself. It will be given to you, or they will give you like a hint as to how to get it, and it takes 2 seconds, okay? So if you flip over to the next page, I have a summary basically of everything we've kind of just looked at. So again, R is a number between -1 and 1. So if somebody tells you they have an R correlation value of 1.2, that's not true. You can't have correlation higher or lower than positive or -1. Next, R can be used on any scatter plot that is linear. So R is useful if the scatter plot is linear. But if the scatter plot is curved, R doesn't mean anything. I can calculate a value for R, but it's not actually useful. Okay? Because R comes from z-scores. If you notice, R doesn't have units because z-scores don't have units. So if they say the correlation R equals 0.7 chickens, that's not right. There should be no chickens. There should be no units. Okay. This one's a weird one. R is completely unaffected by changing units or by transforming data. So meaning, if I had instead of hours studied, I had minutes studied, I changed those values to minutes, it would not change the value of R at all. Also, if I multiplied all of the data by like 2, still wouldn't change R at all. So that's kind of interesting. And then this guy, guys, this is your big one. This is what AP really wants you to know. So let's say I have correlation of 1. I have a perfectly straight line, which means if I study for an hour, I will increase my test score by 10 points. Like definitely, for sure. So 1 hour of studying equals 10 points extra on my test. Correlation does not imply causation, which means if I have a really high correlation, like 0.999, that does not mean that my X value causes my Y value to happen. So even though if I graphed hours studied and test score and I had a perfect straight line like this, I still am not allowed to say that studying longer causes my test score to go up. All I can say is there is a very strong relationship between the hours one studies and the test score that that person receives. I can say there's a connection. I can say there's an association. I cannot say that X causes Y. Okay? And this one's the weirdest one for me. The last one's not going to make sense until we do stuff later in the unit. Changing the explanatory and x and response variables, so switching which one is x and which one is y, does not change correlation. So that means I put the z-scores for hours on the x-axis and the z-scores for y, or for test scores on the y-axis. If I had switched those, I would still end up with the same R value. Why? Well, that's because of what we're looking at. We're looking at z-score of x times z-score of y. Well, if I switch where those are, then this would just be z-score of y times z-score of x instead. I'd switch the order. Well, does that change your answer for multiplication? No. So because of that, changing the explanatory and response variables doesn't change correlation at all. And that just makes sense in real life. If I'm trying to graph the relationship between hours studied and test score, that relationship is going to be the same whether I think hours studied causes the test score or if I think the test score is going to cause you to study for a certain amount of hours. It doesn't matter. That connection's still the same. Okay? And then finally, correlation is the slope of the line of best fit of the z-scores of the data. That shouldn't make any sense to you right now, and it's not gonna for a while, okay? So when I designed this lesson, I sort of designed this as like a two-parter, I think. Let me make sure, hold on. No, that's not what I want. It is not what I want. Yeah, so I designed this lesson as a two-parter, and so I actually saw you guys stopping right now and then continuing the rest of this lesson tomorrow. So if you want to do that, go ahead and do that. If not, then we're going to keep going. So again, I sort of saw this as a two-part lesson. We're at like 31 minutes now and like 45 seconds, so go ahead and pause this, and then you can resume it tomorrow. Or if you're like, no, let's just do it, then all right, here we go. Okay? All right. So to start with this lesson, which is continuing on from last lesson, I am going to draw a bunch of graphs on here and then give you a couple of correlations. And what I'd like you to do is sort of fill in what you think the rest should be. So let me go ahead and draw that for you right now. Pause this real quick, and then I'll have you guys actually do this part of the assignment. All right, so here I have a couple of things filled in. So for example, for the first one, perfectly strong negative, I have r equals -1. What I'd like you to do is I would like you to actually pause this and draw a picture of a scatter plot that would fit this description. So perfectly strong negative, show me what that looks like. And then for any of the problems that have a graph shown, I would like you to estimate what you think the R value would be for examples for a strong negative. So what would the R value be here? So go ahead and sort of estimate what you think it would be. There's no right answer here. There's a good range, but there's no right answer. So I would like you to do that for the top 5, and then we're going to talk about the bottom 2, okay? So go ahead and pause this, either draw me a picture or give me a plausible correlation value, okay? Okay. For the first one, you needed to draw a scatter plot with all of your lines perfectly lined up and heading down, or all of your points perfectly lined up and heading downwards. For this next one, I would give this like a 0.9. Like, it's pretty good. It's close to -1. I know it's negative because it told me it was negative, and it's strong, so I know my value should be close to 1. My next one, moderately strong positive. So the graph's going to look like this. It's not going to look as strong, as closely together as the strong one, but it's still going to be pretty good and clearly heading in a positive direction. So I gave this a 0.8. Pretty good. It's close-ish to 1, but it's not as strong as like 0.9 or something like that. For this one, -0.45. So it says moderately weak negative. So I know the general trend should be heading downwards, but I also know the points shouldn't really be as tightly together as the other two that were drawn previously. So maybe something like this. And then my last one, my correlation R equals 0.3. should in this case be heading in a positive-ish direction, but it should look more blobby, if you will, than the moderately weak negative. So something like this is sort of what we were going for here. So hopefully you're kind of getting the hang of how R values work. To some extent, they're still pretty subjective, but the closer the R value, the correlation value is to 1, the straighter the points are in a line, or the stronger the relationship, as long as the data is linear. Okay, so then let's talk about no correlation and then strong constant, because every year I get this question, every year it's sort of a weird idea. So again, no correlation is going to look like a blob, and there's not, the main giveaway for no correlation for R is equal to 0 or a value close to 0 is if you can't tell what direction the points are going in, then there's no correlation. The correlation is 0. Strong constant, I get this every year. And we kind of talked about this in the last part of the lesson. Well, what if the points are perfectly in a line, but that line is flat? Well, my correlation's still 0. Correlation is trying to tell me direction and strength. In this case, let's say I was looking at hours studied and test score again. What this graph is telling me is that the person that studied for 1 hour is going to get the same test score as the person who studied for 10. Which means, does the amount of hours I study in any way, shape, or form influence the test score I get? No. Or in other words, is there any connection between the number of hours I study and the test score I get? Well, according to this, even though these are perfectly in a straight line, the answer is no. It doesn't matter how many hours are studied. There's no connection whatsoever with the test score. So in this case, there's no correlation, there's no connection. So even though these points are perfectly lined up, it still means that there's no connection between the x variable and the y variable. So if you get a perfectly constant flat line of points, that's still a correlation of 0. Okay? So let's check out the next part, see how you do. So correlation and real life relationships. So I want you to consider each of the following relationships. Really. Okay. And I want you to rank each of the relationships from strongest correlation to weakest correlation. Okay. So we have number 1, the heights of fathers and the heights of their adult sons. So is that a strong correlation, weak correlation? Heights of husbands and their wives, and the heights of women at age 4, and the same women at heights at age 18. So for example, I would take my height at age 4 and compare with my height at age 18. Okay? So pause these, go ahead and put these in order from strongest relationship, strongest correlation to weakest correlation. Okay. So hopefully you pause this. If you haven't, pause it now. Okay. So the strongest correlation is this guy. The heights of women at age 4 and the heights, same women at age 18. Second strongest is the heights of fathers and the heights of their adult sons. And the weakest is the heights of husband and their wives. Why? Well, for the third one, the heights of women at age 4 and their heights at age 18, you're measuring the height of the same woman. So the relationship between those heights should be pretty tight. Meaning, if I'm tall when I'm 4 years old, I should also probably be tall when I'm 18. There should be a pretty direct correlation there. Now, I know some of you might have put the heights of fathers and sons as the strongest correlation, but I will offer you this. Yes, if the dad is tall, probably their kid is also going to be tall, but you got another thing influencing that, and that's mama. So the deal is, listen, people, I'm like 5'2". I'm a shrimp. I'm a midget. My husband is 6 feet tall. We have a son. it's anybody's guess how tall this kid's going to be. So this relationship is going to be weaker than the first relationship because I'm comparing the heights of fathers and their sons. There's another factor in there, which is the mom, and that's going to influence the heights of those sons. Versus this guy, you're just comparing a woman to herself. There's no other factors influencing that. So if you have a short kid at age 4, that human being is probably still going to be short for their age at 18. Okay? And then finally, the heights of husbands and their wives. You could argue, yeah, typically shorter people tend to marry. Well, actually, I would argue that taller people tend to marry taller people. I would argue shorter people tend to marry taller people because they want to balance out those effects, speaking as a short person who married a taller person. But that is the order of correlation. So your strongest relationship is 3, second strongest 1, and then your weakest is 2. Okay? So now we go to finding correlation on a calculator. Okay. Oh, why did that get all messed up? Bummer. Okay. So finding correlation on a calculator, and there's some space on the next page to write the rest of this. So first thing you guys are all going to have to do for me, every single last one of you right now. You are going to have to turn your calculator on. So if you need to pause this and take out your calculator, that's fine. Word, hate you. Okay. So what we are going to do is we have to turn on something called the diagnostic. Okay. So my TI-84s, I'm talking to you. Everybody else, I don't know what you have. I told you to get an 84. You should have gotten an 84. Okay. So you're going to turn your calculator on, and you are going to press second 0. So second, and then the number 0. Okay? And you should get a catalog. The very first thing you see should be ABS. It's for absolute value. We are going to scroll down to the D section, and we're going to look for the thing that says diagnostic on. So you can literally press the downward arrow. Actually, just go ahead and do that. So go ahead and press the downward arrow until you get to diagnostic on. Okay? Once you get to diagnostic on, you are going to press enter. So diagnostic on, press enter. It should then write the term diagnostic on your screen, and you're going to press enter, and you need to see the word done. So you're going to press enter twice, and you are looking for the word done. Now that you have done that, you do not need to do this again unless you change your batteries. Okay? So diagnostic on is just going to help your calculator find R. If your diagnostic is not on, your calculator cannot actually get R. Okay? So now that we have that, the way that we're going to get R is you're going to first put data into L1 and L2. So, hey. So step 1, enter data into L1 and L2. So you're going to enter your data for your scatter plot into L1 and L2. After that data is entered, you are going to press Stat. You are going to scroll over to Calc. And then you're going to scroll down to option 8, which is linreg, and it should say A plus BX. There's another option that says linreg, but that is number 4. You do not want that option. And then you are going to press enter. Once you do that, R should be the very last value at the bottom. So the R is at bottom. So once you do that, it should give you an A, a B. Let's see if I can do this here. Stat calc. I don't think this is going to work for me because I don't think I write things. Oh, I do. Haha. Okay. So once you press linreg, so here, start from the beginning. Once your diagnostic is on, you're going to enter data into L1 and L2. And so if you want to just try this as an experiment, put in L1 1, 2, 3, and put in L2 4, 5, 6. Actually, no, put 4, 5, 7. There we go. Okay. So go to L1 and L2, enter 1, 2, 3, and 4, 5, 7. Okay. So 1, 2, 3. I'm doing it on mine as well. 4, 5, 7. Okay. After you're done doing that, you're going to press Stat, scroll over to Calc, scroll down, or press the number 8. When you press the number 8, it should ask you for an X list, which should be L1. Your Y list should be L2. And then you're going to go down to calculate, leave everything else blank. And when you do that, it's going to give you, it says y equals a plus bx. It's going to give you an a value. It's going to give you a b value. It's going to give you r squared. And then at the very bottom, it should give you r. That's your guy. That's r. That's correlation. Okay? So, hey. Finally, we are going to look at a last example, and I think I am going to have you try parts of it, and then we'll do parts of it together. Okay? So, correlation and outliers, because we got to talk about how outliers influence correlation. So, the figure below plots the average brain weight in grams versus average brain weight in kilograms for 96, average body weight, excuse me, in kilograms for 96 species of mammals. There are many small mammals whose points overlap at the lower left. So part A, it says the correlation between body weight and brain weight is 0.86. Explain what this value means. So I would like you to pause for a second, and I would like you to try to explain what a correlation of 0.86 means about this data. Go. Okay. So a correlation value R 0.86 means that there's a pretty strong positive correlation between body weight and brain weight for these mammals. So in general, the higher the brain weight, the higher the body weight, the higher the brain weight. So that's what an R value of 0.86 means. Hopefully you wrote something like this. If you were actually answering this on an AP test, I'm guessing most of you would say something about pretty strong and positive correlation. The only thing I'm betting a bunch of you would leave out is context. So all you got to do for context, people, is just say the words body weight and brain weight, essentially. So make sure you actually say that. So a perfectly acceptable answer would be my very first sentence. I included the second sentence just for clarification. It would be a great answer to give both, but a perfectly acceptable answer would be my first sentence. Okay? So next, let's talk about our outliers here. So I'm going to argue, and they have them listed here, that there are 4 outliers on this graph. You have your dolphin, human, hippo, and elephant. We are going to first focus on this outlier, the elephant. And so I would like you guys to stop, again, pause, if there's someone with you, which hopefully you're in class, so there are, discuss what effect does the elephant have on that actual value for correlation? So what effect does that elephant have? Does it increase the value for R? Does it decrease it? What does it do? Does it have any effect whatsoever? Okay? So pause this, come up with an answer, and then I'll sort of go through my explanation. All right. So what effect does our elephant have on correlation? Well, the elephant's going to super increase your correlation. Let's talk about why. So for our elephant, both his body weight and his brain weight are way higher than the rest of your mammals. And so because the body and brain weight are so large compared to the rest of the mammals, that elephant's z-scores, remember, because that's how we make correlation, that elephant's z-scores are both going to be huge. And so because both of the z-scores are going to be huge, that's going to increase the overall product of the z-scores. So here's sort of how I would actually write that as an answer. And yes, pretty much all of this would be required if you wanted to get full credit on an AP test. So the elephant increases correlation. Because both the brain weight and the body weight for the elephant are so large compared to the rest of the mammals, the elephant's z-scores will also be large and positive. These large positive z-scores would increase the average product of all the z-scores, which thus increases correlation. Okay? So that's what our elephant's doing. He is super increasing that correlation. So what about the rest of the outliers? So how would the correlation change if the hippo, dolphin, and human measurements were removed? So go ahead and pause. Try to answer that question. So what would happen to the correlation? How would it change? Would it increase? Would it decrease? What's going on? Okay, so pause and answer that. Okay. So hopefully you noticed this, but if I took out the dolphin, human, and hippo, so if I took out these three, if you notice, even as I'm circling them, as I circle these three, you should almost notice a negative correlation, meaning the smaller your body weight, the higher your brain weight. If I took out those three, then that would actually make my correlation much stronger, because I would take out all three outliers that don't follow the overall pattern, which is the higher the body weight, the higher the brain weight. Okay? So I said something like the correlation would increase or become stronger. That says closer to 1. If these were removed, since they don't follow the overall pattern of the rest of the mammals. Okay? And then finally, if we added an extinct mammal such as the woolly mammoth with an approximate weight of 2,700 kilograms and approximate brain weight of 550 grams, what would be an approximate value for the new correlation? So I'm adding in our woolly mammoth that's way over here. He's got a body weight closer to 2,800, so 2,700, but his brain weight's close to 500, so I'd add that in. So if that point was now part of this graph, what would be an approximate value for the new correlation? Oops. So if I'm starting out with a correlation of 0.86, what could a new value for correlation be if I added in that outlier? It really doesn't matter, folks, as long as that correlation is farther away from 1. So it might be 0.71 now instead. So a new value might be 0.71. It might be 0.5. It might be 0.4. The point is, I'm adding in an outlier that is not following the pattern of the overall data, and this outlier is a big boy, which means his XZ score is going to be huge, and his YZ score is going to be small. That means this is going to be a very, very, very negative product of your Z-scores, and that's going to significantly bring down your correlation, okay? So for the last answer, really any answer would be fine as long as it's less than 0.86, okay? All right, folks, so that's all for these two lessons together. So this second half of the lesson was designed to be a little bit shorter in hopes that you would try your homework and kind of get an idea of how that goes, okay? So hopefully these are going okay. We have 4 more recorded lessons for this section. Some of them are multiple days, some of them are not. But anyway, this is sort of an intro to linear regression. So hopefully you've enjoyed it so far. All right, y'all. Peace.